Good evening. Analytic geometry is our final topic of the semester. So let's say we're given some kind of path. Let's call this our path. And for the sake of argument, we're just going to say we're traversing it in this direction. Doesn't matter. That can't be represented as a function, can it? We can't say that's y equals f of x. Fails the vertical line test. We can't say that's x equals f of y. It would fail the correspondent of that, the horizontal line test. However, we still want to be able to analyze this curve. Right? We still want to be able to do things like find the length of that walk, or at a specific point, find the slope, i.e. find the velocity. How do we do this? We do this using parametric equations. Which we can also think of as just a two-dimensional vector. However, for some reason, the term vector is saved for Calc 3. So all the arithmetic on vectors will be covered in Calc 3. For now, we can just kind of think of this as a two-vector. Well, let's take some point. At that point, it's going to have some x-coordinate, some y-coordinate, right? In fact, every single point along this path is going to have an x-coordinate and a y-coordinate. But what if we can find a function for both the coordinates? That is, x is actually a function of t and y is actually a function of t. This is the idea of a parametric equation. So you can write it as ordered pairs, x of t, y of t, or as a set of parametric equations, x equals some equation and y equals some equation. T would be our parameter. And again, it doesn't have to just be T, it can be anything. You typically don't want to use the same variables as we're using in the parametric equation, so you don't want it to be like x or y. T is common. Time. Theta is also commonly used. D would be the parameter domain. And if you write it as the ordered pair C of T, we call that a parameterization. The curve that's represented by C of T called a parametric curve. You can come up with some really interesting curves with parametric equations. What I'm going to focus on first is plotting several parametric curves. Okay, and then with any time left over, we'll look at the My Open Math assignments and see what kind of problems that gives. Right. I do recommend you watch the video. I believe the video goes over how you can write any curve as a parameterized curve. It also goes over a technique known as removing the parameter, eliminating the parameter. So if you're giving a parametric curve, it may be possible to write it as a function y equals f of x. Not every curve can be, like this one, for instance, can't be. But some can, and it goes over that method. And so first up, we're going to have a curve that's given by 4 cosine of t, comma 2 sine of t. We'll plot this over 3 intervals, 0 to 2 pi, 0 to pi, and then minus pi over 2 to pi over 2. So I use, obviously, Mathematica a lot. But if I'm not mistaken, if I remember correctly, you can also do this on a TI Inspire. If you have Scratchpad open, we're just going to come over to Graph. I have to remember how to do it. And, there it is. Hit Menu, Graph Entry, gives you several options. One of them being parametric, so we're going to select that. Four times cosine of t. It was then 2 times sine of t. That is 0 to 2 pi. Just write out 2 pi. Don't know if it's going to make a difference. And what do I want? What do I want my t step to be? I don't know. Pi over 4.
What's t step?
What points are going to plot? What t values is it going to be plotting, basically? That's not good. I don't like how that went. So I'm going to try and adjust my t step. That was already at 0.13. What if I do pi over 2 instead? Now it's still going to give me that. This is just a label. I don't need it. Now it's deleting that. I don't know why. Yes, I do. Because that 6.28 is not exactly 2 pi, so it's not giving me everything. Let me do 7.28. Perfect. Just go slightly over 2 pi so I can get the full picture. All right, so you can do it on calculator, not as powerful, not as useful as you see. Mathematica, much more powerful. But for exam purposes, this will be fine. All right, now let's look at how we would do it in Wolfram. Command is parametric plot. In braces, you then just do the ordered pair. What is x? And what is y? You then need to input the parameter domain. That is what it will give us. Right, so that is the bare minimum that you need for a parametric plot. You just need the parameterization and your domain. But of course, there are several options we can do. The main one being, I don't like the color. I'll just go ahead and label the axes. And let's do just go ahead and label this as well. Called 0 to 2 pi, just so we know. Do you recognize that shape? you should. Fairly certain you studied it a little bit in geometry. It's called an ellipse. By the way, a circle is an ellipse. And it's just an ellipse in which the semi-major and semi-minor are the same. What I'm going to do right now, I'm going to copy this. If it lets me. Perfect. Fine. No reason why I hate the cloud version. Every parametric curve has a direction. The direction of a curve is just simply the direction in which t is increasing. We can show this on the plot using Wolfram. And it goes under plot style. The arrowheads command. I'm going to plot a set of arrows. So each arrowhead is an ordered pair. The first number is the size of the arrowhead. I'll start with 0.05 and see how that works. The second number is going to be the position. It's a number between 0 and 1. I'll start with 0.15 and see where that puts it. I'm going to do 4 of them. Now, if I execute this, it shouldn't do anything. Yeah, won't do anything yet, because I have to add another command. To tell Mathematica to change the lines into arrows, so it will plot arrowheads. There's the direction, counterclockwise. Not really that important for this course. Extremely important in Calc 3. Or if you're studying actual motion, right? If this curve represented motion, then the direction would be important. Next up was 0 to pi. Oops. And I'm just going to ignore arrows from now on. Not really concerned with the direction. Before I actually execute this, what do we think the curve's going to look like?
It'll be smaller than the previous one. It's from 0 to pi, while the other one is from 0 to 2 pi.
Define smaller.
Smaller as in like both length and width.
Length and width make no sense for an ellipse.
So what would you be parametric then? Because when I think about it like from top to bottom and from side to side.
In an ellipse, you have semi-major and semi-minor, but it doesn't one way or the other. You could call it horizontal width and vertical width if you wanted to, I guess. If that's how you're defining, then no, it's not going to be smaller. Well, you're right. Cutting the domain is going to have an effect. Everybody else wants to take a wild stab in the dark? Oh, what a shame. It's the upper half of the ellipse. Right, much like 0 to pi is the upper half of a circle. Right, remember, a circle is an ellipse. And last thing, we're minus pi over 2 to pi over 2. All right, now from the last problem, what do we think this is going to be? Think of it in terms of a circle. Minus pi over 2 to pi over 2 corresponds to what part?
Is it gonna be now that instead of it being cut in half, horizontally, it's gonna be cut in half vertically?
Which side?
We're gonna have the right side and we're not gonna have the left side.
You don't sound confident.
But I'm not too sure.
How much would you wager on that?
If you're willing to bet against me, I'm willing to wager 100%.
Oh, you're going all in.
Yeah. But
It's the right half of the ellipse. So ellipses, is that the proper plural? Ellipses, ellipsi, I don't know. Ellipses, whatever it is. Very common. I'm sure you've heard this term before. Elliptical orbit. Right, the planets are in elliptical orbit, not circular orbit. Which means there is a point in the orbit at which Earth is closer to the sun than any other point. What do they call that? Is that the aphelion? No, aphelion is furthest from the sun. What's the other one? Perihelion, that's what I thought. Then the perihelion is the point at which it's closest to the sun. This is also because the sun is not actually at the center of the ellipse. At least I don't think it is. Could be wrong. But I think there's only one aphelion and one perihelion. If the sun was truly at the center of the orbit, then there'd be two of each. Your semi-minor would be the perihelion, your semi-major would be the aphelion. But I think there's only one of each, which would mean that the sun isn't at the center. The curve secant of t, comma, tangent of t, minus 1.5 to 1.5. That's what this parametric curve looks like. We're starting off with some boring curves. Don't worry. I have really interesting ones coming up. This one's really boring. 2t plus 3, comma, t squared minus 1 over the interval, negative 2 to 2.
Is it supposed to be 2t plus 3, comma?
Mm-hmm.
Yes.
So I said this one's really boring. It's just parabola. Okay. This curve I actually like. This curve's fun. T minus sine of t, comma 1 minus cosine of t. I'm going to do it over 3 intervals, and then I'm going to manipulate and extend the interval to go longer to show you what this does. We're going to go 0 to 2 pi, then to 3 pi, and then to 4 pi. That's a parametric plot. We have t minus sine of t. And then what was it? 1 minus cosine of t. Start with 0 to 2 pi. So there's what it looks like from 0 to 2 pi. Okay. Let's go up to 3 pi. We'll take a guess on what extending out to 3 pi is going to do. Let you think about it. Right, and then I'll execute it, and you can determine if you're right or not. But wait. Oops. So you can then probably guess what's going to happen if I go out to 4 pi. So go 0 to A. Get rid of the plot label. A. Let's manipulate A from 0 to I don't know. 20 pi. Don't want it to change by. I want to change by pi over 2 each time. I don't know why it's doing that. It won't let me actually play it. Okay, this actually is very disappointing. So I'm going to cheat. I'm going to use the desktop version because that will actually let me run the animation apparently. Okay, so at 0, it's not going to let me do anything. It gives an error. I don't know why, but it does. This type of curve, it's called a cycloid. Uh-oh. Why did you stop? I didn't tell you to stop. Oh, you crashed. Did you? No, you just stopped for some reason. I don't want that error to keep popping up, so let me change this to a really tiny number. Okay, so this curve is more common than you would think. Imagine a tire. You put a dot on the tire. as the tire spins and you plot the motion of the dot with respect to the ground, the cycloid. And this will just keep going forever and ever and ever. If you were in a perfect environment, you threw a ball, and you're somehow in a world where that ball never lost energy, so the collisions never took energy away from it. That would be the model for the trajectory of the ball. Right? Because it would never lose height because it's never losing energy. It would always go to the exact same height with each bounce. Okay, so sadly you were a bust, but now we get into the really interesting ones. So we're going to plot two different curves. One where all the plus minuses are plus, and then one where all the plus minuses are minus. So let's see. Start with the positive. We have 2 cosine of t plus cosine 2t, 2 sine of t minus sine of 2t, t from 0 to 2 pi, and let's call this the positive one. So there's the curve. Now, Replace the pluses, the plus minus, right? We did positive before, now we're gonna do the negatives. By changing those positive to negative, what do you think is going to happen? Just a real minor change. So again, just picture what it's going to do in your head, and we'll see if you're right. Is that what you thought? Like an apple without the stem. Trying to keep it rated PG. Now we're going to replace the 2's with 3's. Let's see how this changes things. Right, so again, that was when we had 2's. What do we think it's going to look like if we replace 2 with 3? It's going to almost resemble a diamond, which is just a rotated square. I think it's a square rotated 90 degrees. Right, so now instead of -2, we're going to have -3. So think back to what the last problem did. We're going to replace the positive with negative. And try to picture what's going to happen here. Let's grab the 10. So this is what's happening as your value of that constant increases. Let's go even further out. Say 15, and I don't actually want to start at 1, I want to start at 2. Let's make it interesting, 20. I mean, you kind of see the general pattern on what's happening. All right, we'll look at the negatives. Similar kind of idea. Which means you should be able to kind of visualize what this curve will look like. Oh, actually, wait a minute. That is a typo. So let's fix that. There we go. That should be a minus, not a plus. All right, now it's a completely different idea. Not super completely different. That was 9 cosine of t minus cosine of 9t. 9 sine t minus sine 9t. T from 0 to 2 pi. This has a name. This is known as an epicycloid. Similar structure. Ah, yes. This is a hypocycloid. And I saved the coolest for last. Cos t plus 5 cosine 3t, 6 cosine of t minus 5 sine of 3t. Really like this one. This is a hypotrochoid. That's an interesting curve. Imagine traversing that path. Actually, probably not a terrible path to walk, like it's in a park or something. And these are just parametric. We'll see some even cooler curves next week. Questions on the plots before I move on. I think there's only one assignment for this. Yes. Well, that we're not going to be able to do. Okay, then. Not going to be able to do those. Oh, is this really all just calculus? Oh dear. Yeah, it is. It's all calculus. Oh, okay then. Which can just go away. No, you're going to make me update, aren't you? Oh, okay. Should try to do some parameter elimination, looks like. They want us to sketch the curve by eliminating the parameter. I don't think I'm going to worry about sketching as much as eliminating the parameter. So here's the idea with eliminating the parameter. Pick either x or y. And we're going to solve that chosen for t. Well, y would be, for number one, y would be the easiest one to solve, right? So t would be y minus 1. Take that t, plug it into the other equation. This will now give us, in this case, a function, x in terms of y. It'll be what? Y squared minus 1. What kind of curve is that? So if we were to go and sketch that. What kind of curve would that be?
Is it going to be the parabola with like shift to the right side or no?
So I agree it's a parabola.
So like the x-axis is going to be in each.
It's not going to be shifted to the
I
right.
can shift like this.
Oh, rotated?
Yeah.
Yeah, it will be rotated.
And it's going to be 1 point like down.
Will it be one to the left?
It's going to be 1 to the left. Remember, this is x of y, not y of x.
Right.
If it was y of x, it would go down.
Left, no right.
Left, in this case. Right, again, you're thinking y of x, where you shift the directions if you're translating horizontally. Because this is y of x, you have to alter your thinking. Instead of the minus 1 being up, down, it'd be left, right, and the sign tells you the direction left. I don't know, something like that. That's probably what it would look like. You could always check it. I'm too lazy. Pick one. And I don't know, X. Oops. This one's going to be a little bit tougher. But I'll make do. T would be, again, not quite the inverse cosine of x. Because that's only going to give me half of my domain T. Let's just continue on and see what happens. Plug it in, y is going to be sine of the inverse cosine. What is sine of the inverse cosine of x? That would be x. That would be 1. What's this? Square root of x squared minus 1? No, 1 minus x squared. Other way around. So that would be y of x is the square root of 1 minus x squared. But that was only for 0 to pi. What kind of shape is that? So if I were to stop there, what shape is that? Hmm.
We can't pass x equals 1, get it?
Why can't X be 1?
No, it can be, well, it can be more than 1.
Can't be, right?
So it's,
So X can't be larger than 1. I definitely agree with that.
I would,
There's another value. There's another range that X can't take.
so between 0 and,
X can be less than 0. Can't be less than -1. Oh, you don't recognize that. It's a shape you may want to recognize. It's going to be very important. That's a semicircle. Specifically, it's the upper semicircle of radius 1. Right, but again, that is only 0 to pi. We were told t goes 0 to 2 pi. Which means we'd also need the lower portion of the circle. Right. What we can do from here is square both sides. Which would then give x squared plus y squared equals 1, which is the entire circle of radius 1. Right. Doesn't matter which one we pick here, right? Either x or y, because they're both fairly simple to solve for t. So I just chose x. We're going to get y is x over 2 minus 3. What kind of curve is that?
A line.
It's just a line. Specifically,
So we go into the x-axis, mine's down.
what's the slope?
1/2.
Where's it going to cross the y-axis?
-3.
I don't know, maybe something like that. Just a sketch. This last one. We'll find that t is 3 minus x. Y would then be 2 times that. Minus 3, it's what? 6 minus 3 is 3. Minus 2x. What kind of curve?
A line going.
Line, slope, -2, y-intercept at 3. But is it the entire line? No, because here we're specifically told t only goes from 1.5 to 3. So t is 1.5, x is 1.5. And when t is 3, x is 0. So it's the line from x equals 0 to x equals 1.5. All right, so I don't know, 3. And when x is 1.5, y is 0. So this curve is actually a line segment, right? It's not a line. See that? Okay, so that's just all that, same stuff. And that's just naming basic, okay. So we get the gist of eliminating the parameter. Yeah, I think I will stop there. So begin working on the assignment 23. So, I forgot. Assignment 23, I just looked at that. That's all calculus. So no assignment to work on this time. We won't be able to do 23 until after we look at the calculus of parametric curves on Monday. So we're going to look at a few things. We're looking at slope, so dy dx, given a parametric curve. We're going to look at arc length. Going to look at I don't think it's area. That's arc length. Maybe surface area? That might be the other one I look at, surface area. But definitely derivatives, and definitely arc length. I think there's a third one. I think it's surface area. I don't think it's area. I don't think it's area under curve. I think that's for polar. I think it's surface area. Have a wonderful weekend.